Okay, so unit 2 of linear algebra starts from this chapter, canonical forms, and in your book linear algebra precise, this is third chapter and section 2 is characteristic equations and eigenvalues and vectors. So this is your topic. Now I will define this thing. Lambda, eigenvalue. First of all, definition, eigenvalue. So you say let capital T from V to V be a linear operator. Here. VF is vector space. Then lambda belong to F is said to be eigenvalue of capital T if there exists V which is non-zero in V such that PV is equal to lambda V. So what it says that you have a vector space, and this is a linear transformation is T, and you have a field F, and it says that here you have a vector V. This V should be non-zero, and when you find its image is lambda V, and you say TV is equal to lambda V. I hope the definition is clear to you. So you say that this is eigen value and this V belong to V which is non-zero is called eigenvector. Now theorem is, it says that next part is, you say TV is equal, okay, lambda is eigenvalue of capital T corresponding to eigenvector V. So both EV are represented in same way, but you know that lambda is value and V is vector. So you say TV is equal to lambda V, fine. But see, V is equal to IV always, where I is identity operator. So this is TV is equal to lambda IV, so that T minus lambda I into V is equal to 0. This means that V is a non-zero vector in V which have image 0, This means that T minus lambda I is not 1 1. Why we have done this lemma? Lemma is T is 1 1 if and only if kernel of T is equal to 0, i.e. TV is equal to 0 implies V is equal to 0. So this is your lemma. We did this yesterday, and you say T minus lambda I will become 0 when we put a vector V in this. This means that a non-zero vector is making T minus lambda I equal to 0. This means that T minus lambda is not 1 1, implies T minus lambda I is not is singular. Okay, you have this lemma. Lemma says T is 1 1 if and only if T is onto, if and only if T is iso, if and only if T is non singular, if and only if T determinant is non-zero. I hope you listened that recording of prerequisites of unit 2. So this is your theorem that you are using. So you say T minus lambda I determinant is equal to 0. T minus lambda I determinant is equal to 0. So T minus lambda I determinant is equal to 0 implies T minus lambda I determinant, T minus lambda is non-singular, implies it is not 1 1, implies there exists a non-zero vector which makes T minus lambda I is equal to 0, implies T minus lambda I into V is equal to 0, implies TV is equal to lambda IV, implies T is equal to lambda V, implies T is eigenvalue of T corresponding to eigenvector small v. So this result is bidirectional, and theorem is, statement is, lambda is eigenvalue of capital T if and only if T minus lambda I determinant is equal to 0. This is your theorem. I hope this thing is clear to everyone. Is this clear to you? Please tell me. Next part is remark, or you can see T minus lambda I determinant is equal to 0 is called characteristic polynomial equation of capital T, and T minus lambda by himself is called characteristic polynomial only. If it is equal to 0, then it becomes equation. If it is not equal to 0, then it remains a polynomial. So this is your remark. Now numericals. How you approach a numerical? Some linear transformation from V to V is given to you. Step 1, find matrix of linear transformation. Find matrix of linear transformation with respect to any basis. We will do a theorem 5 minutes from now, which will prove that you take any basis of vector space for a linear transformation. When you find the matrix will change, but its eigenvalues, its characteristic equation will not change. It doesn't depend on the basis. Find matrix of linear transformation. First of all, step 2, find this thing, characteristic equation, and solve that. When you solve that, you will get eigenvalues. For example, matrix of linear transformation is capital A. Next step is step 3 is to find vectors. So to find vectors, what we do? We use A into AX is equal to lambda x, or you can say AV is equal to lambda V, because we are doing linear algebra. We can use this representation also. So this is A minus lambda I into x is equal to 0. You solve this and you will get the eigenvectors. I hope this thing is clear to everyone. And let me write a question. Question is, this is given in your book. Question is given to be, okay, one second. Question is given to be, okay, this is T of x, y, z is equal to 2x plus y, comma y minus z, comma 2y plus 4z. So how to find matrix of linear transformation? This is, you say T from R cube to R cube is given, and R cube has basis. We know it has basis 1 0 0, 0 1 0, and 0 0 1. So this is your basis. Now to find matrix, step 1 is to find matrix of linear transformation, what we do, we find T100, T010 and T001. I hope you know this. When you will put this, it will become 200, then it will become 112, then it will become 0, -1 and 4. Then you will find, then you will represent it as linear combination of bases, and it will be 2 into E1 plus 0 into E2 plus 0 into E3. It will be 1 into E1, 1 into E2, 2 into E3. Then it will be 0 into E1 minus 1 into E2 plus 4 into E3, so that T with respect to B basis of R cube will become 2, 0, 0, 1, 1, 2, 0, -1 and 4. So you have this 3 cross 3 matrix. This is matrix of linear transformation. First step is done. Now we want to find the characteristic equation. How we find the characteristic equation? You know this. We say this is equal to A, say, then you find A minus lambda. I think you can do rest of the things. These are from BSc SEM 2. Sorry, BSc SEM 1 and SEM 6. I hope you can do this part. I will just write for once. This is A minus lambda I into determinant is equal to 0. It will be 2 minus lambda into 1 minus lambda into 4 minus lambda plus 2 is equal to 0. So you have this equation 2 minus lambda, lambda square minus whatever. This is 4, 6, 5. Lambda plus 6, so lambda is equal to 2 comma 2 comma 3. You have these three eigenvalues, then you find eigenvector. You take A minus 2i into capital X is equal to 0, solve this, and A minus 3i into capital X is equal to 0, solve this. You will find the eigenvectors. I hope you can do this part. Next thing is eigenspace of a eigenvalue, eigenspace of a eigenvalue. What I am trying to say in this is, let T from V to V be a linear operator and lambda be its eigenvalue, and lambda be its eigenvalue. Then E lambda is eigenspace of eigenvalue, is defined as collection of all those vectors of capital V which are eigenvectors of capital T with respect to eigenvalue lambda. This means that V belong to V such that, okay, what I am trying to say is, this is your V, this is your V, okay, this is your V, this is your V, and this is a vector V, and this is your linear transformation T. When you apply T, it becomes lambda V. You have another vector, for example W. You apply T, it becomes lambda W. You have this vector, this becomes lambda into, for example, this is K, this becomes lambda K. So collection of all these vectors is called eigenspace of lambda. Okay. So we belong to V such that TV is equal to lambda V. Such that TV is equal to lambda V. Now theorem is E lambda is subspace of capital V. Is subspace of capital V. Now one more thing is, when you say that this is collection of eigenvectors, when you say that this is collection of eigenvectors, 0 cannot be eigenvector. So when you define E lambda, you say we add 0 vector in this. This means union 0. Union 0. Okay. So you say E lambda is subspace of V, because if we want to make subspace, we need 0 in the subspace. So E lambda want to become subspace. How you prove this thing? First step, you prove that E lambda is not equal to 5. First step, E lambda is not equal to 5. Second step, you say if V comma W belong to E lambda, then so therefore alpha V plus beta W also belong to E lambda. Hence, E lambda becomes a subspace. I hope you know how to prove a subspace to be a subspace. Okay. First of all, see, you want to prove that this is a group, this is a group, this is its small part. So, for example, H, you want to prove it to be a subgroup. First, prove this is non-empty. Then take two elements from X and Y from H, and prove X, Y inverse belong to H. So these are steps that we need to follow. So you have a ring. This is an ideal. So you say, first of all, this is non-zero. Then you say you have A and B element here. You say A minus B belong to it, A into B belong to it, R into A belong to it, A into R belong to it. It becomes an ideal. You have a field. This is field and this is subfield. So non-empty, AB inverse, A minus B, A plus B, whatever. So this is the process of proving the structures. Now, you take E lambda, and this is your set. See, this is your set V, this is your set V, this is your linear transformation T, this is your set E lambda, and this E lambda want to be a subspace. First of all, we need to prove that it is non-empty. Now, the element which will surely be inside this E lambda is 0, because you specially entered this element 0 in the set. So you say 0 belong to E lambda, and T0 is equal to 0 implies T0 is equal to lambda 0. So this 0 vector satisfies this theorem, this thing, this relation. So you say 0 belong to implies, sorry, T0 is equal to 0, T0 is equal to lambda 0 implies 0 belong to E lambda, implies 0, E lambda is non-empty. Now you take two elements are V and W, they belong to E lambda. If they belong to E lambda, this means TV is equal to lambda V, because the element which will be inside E lambda will satisfy this result, TV is equal to lambda V. So you say TV is equal to lambda V and TW is equal to lambda W. Now we want to prove that alpha TV plus beta TV, alpha V plus beta W belong to E lambda. Now how to prove this? Where alpha and beta came from, alpha and beta belong to field, they are scalars. So you say now alpha comma beta belonging to F, T of alpha V plus beta W will give alpha TV plus beta TW. How? Why? Because T is linear transformation. We know this. So this TV is lambda V and this TW is lambda W, implies this is alpha into lambda V plus beta into lambda W. This says lambda into alpha V plus beta W. So what I am trying to say in this is, this is your E lambda. This is your E lambda. V goes to lambda V. W goes to lambda W. when I find alpha v plus beta w, it goes to lambda into alpha v plus beta w. So this means that this element also belong to E lambda. Hence, this E lambda becomes subspace. Becomes a subspace. I hope this thing is clear to you. So this thing becomes a subspace. Next one is algebraic multiplicity and geometric multiplicity. Algebraic multiplicity AM and GM. Algebraic multiplicity and geometric multiplicity. What it says is, see, algebraic multiplicity of an eigenvalue is defined as number of times the eigenvalue exists as root of characteristic equation. For example, the numerical that we did when we found the characteristic equation. The characteristic equation looked like 2 minus lambda square minus 5 lambda plus 6 is equal to 0. When we solved this thing, we found lambda is equal to 2 comma 2 comma 3. So if I ask you gm of lambda is equal to 2, am of lambda is equal to 2, algebraic multiplicity of lambda is equal to 2, you will say that lambda is equal to 2 exists as the root of characteristic equation twice. So its algebraic multiplicity is 2. In the same way, you have algebraic multiplicity of lambda is equal to 3, and you will say that it exists only once as the root of characteristic equation, so its algebraic multiplicity is 1. So this is one definition. Now next is geometric multiplicity. Geometric multiplicity of an eigenvalue is defined as number of linearly independent eigenvectors that lambda gives with respect to linear operator. Or you can say geometric multiplicity is dimension of E lambda. So what happens is, you have this numerical. One second. In the numerical that we did, when we find the characteristic equation is this: for lambda is equal to 2, when we find eigenvectors, it comes out to be 1 0 0, and for lambda is equal to 3, when we find eigenvector, it comes out to be 1 1 and minus 2. So what I am trying to say is, when you find gm of lambda is equal to 2, geometric multiplicity of lambda is equal to 2, you say that geometric multiplicity means how many linearly independent eigenvectors an eigenvalue is giving. Okay, so when I ask lambda is equal to 2, lambda is equal to 2 says I will give only one eigenvector, so its geometric multiplicity is 1. In the same way, when I ask lambda is equal to 3, it says I will give only one vector, so lambda is equal to 3 has geometric multiplicity 1. I hope this thing is clear to you. So we have a result. Result says that for t from v to v, lambda being eigenvalue, gm of lambda will always be less than am of lambda. Geometric multiplicity will always be less than or equal to algebraic multiplicity. So for the numerical that we did, lambda is equal to 2 is eigenvalue. When I find its algebraic multiplicity is equal to 2, when I find geometric multiplicity, this thing is equal to 1. This means that lambda is equal to 2 itself occur as the root of characteristic equation twice, but it gives only one linearly independent eigenvector. And for lambda is equal to 3, algebraic multiplicity is 1 and geometric multiplicity will always be 1. If it is 1, then it is 1. See, you say algebraic multiplicity is less than, geometric multiplicity is less than or equal to algebraic multiplicity. Now, if lambda is equal to 2 has algebraic multiplicity 2, then geometric multiplicity has two options. It can be 1 or it can be 2. It cannot be equal to 0. 0 means eigenvalue is not giving any eigenvector. This doesn't make any sense. So you have two options, either it will be 1 or it will be 2. In the same way you have for lambda is equal to 3, you have algebraic multiplicity 1. So geometric multiplicity needs to be less than or equal to 1, so it will be 1, it cannot be 0. Okay, so if you have algebraic multiplicity 1, then geometric multiplicity will surely be 1. In the same way, when you have algebraic multiplicity 2, geometric multiplicity can be 1 or it can be 2. No. Now please remember this thing, this theorem or this result, whatever you say, is basis of this thing. This thing is foundation of this chapter. This chapter includes characteristic equation and eigenvalues and eigenvectors. Then next topic is diagonalization. Then you have triangularization. Then you have Jordan form. Then you have that rational canonical form. So this theorem is the basis of all of these things. Okay, and we will be doing this. We will be continuing this thing.